Welcome to your class in Organic Chemistry. I am again your teacher in this chemistry subject, and I would also like to congratulate you for passing the first chemistry subject for college, that is Inorganic Chemistry. I would like to introduce again myself. I am Miriam Javier of the College of Teacher Education of the University of Northern Philippines, Again City. For this semester, your subject is organic chemistry. Now, as a review, let us try to discuss again what is chemistry. Of course, you have learned that chemistry is the study of the composition, structure, and properties of matter. In this case, we will focus on organic matters to study its composition, structure, and properties. Also, the processes that matter undergoes will focus on organic matters and the energy changes that accompany these processes. So just as the same, your organic chemistry will deal with the processes and the energy involved. So the matter here is your organic matter. So your organic chemistry also focuses on the different fields of chemistry. You could see here all the concerns of organic chemistry for community, health, environment, medicine, industry, sciences, teaching, research, and of course you deals with organic chemistry. What is organic chemistry all about? Organic chemistry is the study of most carbon-containing compounds. So it could be as simple or as beautiful as this, and it could also be as complex as your DNA molecule. Your DNA molecule is actually loaded with a lot of carbons. And also to remind you, my dear student, this is not just a simple drawing of the snowman, but is actually an illustration of an organic compound. And these particles here are not just simply drawings, but these are actually illustration of simple organic compound. So this could be CH, this could be your water molecule working or dealing with this complex organic compound. You might have taken this already, the aspirin. This is the formula of the aspirin that is used in the treatment of simple pains. But our FDA had recommended that aspirin should be limited in terms of utilization. And then this is nylon. Nylon. We are more familiar with nylon with the rope that is made up of nylon. But there are also some fabrics that are made up of nylon. And this is just a part of the repeating unit of nylon 6.6. So you could have still other this structure bonded to this part of the structure. So it is called repeating. You could add here some more or you could add it here. And then as a lesson starter, let us try to make a review of where you are in your own home. Your own home provides you a lot of examples of organic matters or carbon-containing matters. Okay, the question is, what are the objects in your room related to the study of organic chemistry? For this time, what are the objects in your house related to the study of organic chemistry? If you are inside UNP, the question might go this way. What are the objects in your classroom related to the study of organic chemistry? The next question is, how many of your daily activities are related to organic chemistry? This could serve as your assignment to be passed in your Google Classroom activities. So you try to travel inside your own home from the door. The door itself, if it is a metal, of course, it is painted with something that is organic. So the doorknob itself that allows you to enter is protected with organic matter. Or even the door itself is made up of wood, it is made up of organic matter. So anything that is made up of nature is actually made up of organic compounds. Anything that are made up of plastic are made up also of organic compound. Any fiber that you could see, a cloth or a piece of paper, inside your room or inside your home are organic matters. Even the vegetable that you are planning to eat, or even the snack food, or even the soft drinks, they are made up of organic matters. Even the laptop that you are looking right now, or your cell phone that you are looking right now, most of its content are made up of organic compounds. So you have to try to look into what are you doing every day? What are the activities that you are doing that are related to organic chemistry? If in the early morning or just when you have get up from the bed and you want to brush your teeth, the bristles, the handle of the toothbrush are organic compounds. The toothpaste itself and its container might be organic compounds. So cleaning yourself deals a lot of organic chemistry. Nourishing yourself deals a lot about organic chemistry. Going out, the gasoline used by the tricycle or your vehicle are also made up of organic compounds. Now, why do you study organic compounds? Most of the things that are alive or that came from life are made up of carbon. So, as if life is built on carbon. All cells are actually made up of carbon, whether it is an animal cell or a plant cell. 72% of the cells are made up of water, but 25% is made up of carbons. The remaining 3% are your salts or the inorganic compounds that you have learned in your Chem 1. But what you are going to be looking at this semester are actually the carbon compounds. This could include your carbohydrates, protein, lipids, fats, vitamins, nucleic acid, polymers of organic compounds, acids, bases. They are made up of carbons. Now, where are the carbons? Where can you see the carbons? From the pictures itself, you could already determine, or maybe you have already an idea where you could see a carbon or where you could meet the carbon. The carbon are found in the atmosphere, the earth crust, and of course, all living organisms are made up of carbon. Inside the earth's crust, they are bonded with the different minerals. In the atmosphere, they could even be your pollutants. They could be the carbon monoxide, they could be the carbon dioxide. And these are still carbons found in the atmosphere. They are also present in fuels like your wood, charcoal, and even the coal that is used to produce coke. The coke here does not refer to your soft drinks, but rather to the coke that is used as an energy for uh, fuel for fuel. Petroleum provides you carbon, the natural gas, biogas, Mars gas. All of these are converted into energy, and some of which will produce pollutants that could lead to the global warming. Uh, Carbons are also present in hydrogen carbonates. They are also found in precipitate as carbon. So this could be found as your diamond, which is a pure carbon, the graphite, and also the polarites. Now this is your carbon. Your carbon has a symbol of C with a atomic number of 6, and a molecular weight of 12.0107 grams per mole, or just simply 12 grams per mole. And in front of you is the structure or the distribution of the electrons and the neutrons found in carbon. The freezing point of carbon is 3,500 degrees centigrade. The boiling point is 4,827 degrees centigrade. It has versatile building blocks. Actually, they are building blocks of all the macromolecules that you will be learning in biochemistry. And these are also some examples of carbon compounds of industrial importance. You have the graphite, both the alpha and the beta. This is a picture of a graphite. And then the diamonds, and also the polyurines. The one that is used in this dome is made up of carbon. And of course, we have also white carbons. It is a carbon that is powdery white in color. Okay, these are the basic chemistry of carbon. It has an electron configuration of 2s2, 2p6. And the atomic radius is 77. The oxidation states are 4 and 2. Of course, this is how you have drawn your carbon electron dot, and this is how you have drawn also the electron shell distribution of carbon. And this is already the geometric structure of a crystal carbon. All of these things you have met already when you were in your grade school or your high school. However, there are different classifications of carbon atoms. They could be primary carbon atoms, secondary carbons, tertiary carbons, and quaternary carbons. It all depends upon the number of carbon present in a certain compound. So this is an example of a primary carbon that is denoted by one carbon. It is also called the terminal end carbons. They are found in straight chains and they are covalently bonded to one carbon. So this one is a primary carbon. This one is also a primary carbon. Of course, this is not a primary carbon. So this primary carbon is attached to one carbon. This carbon is also attached to one carbon, but this carbon here is attached to two carbon. So this is not a primary carbon. Only these two here are primary carbons. And then you have the secondary carbons. The secondary carbons are donated by two carbons attached to such carbon. This is a carbon attached to one, two carbons. You will come to know the formula eventually later on. Don't be excited. And then for the tertiary, one carbon is attached to three carbons. You have the one, two, three carbons. And of course, they share the same group of or pair of electrons. So they are covalently bonded to 1, 2, 3 carbons. And then you have quaternary. The carbons that are attached to four individual carbons or elements are called quaternary carbons. Okay, carbons are illustrated in geometric pattern. This is a carbon, this is a carbon, this is carbon, this is carbon. All of these are your CH4. Carbons are versatile building blocks. The reaction of one carbon to another carbon could mean an interplay of the adhering molecules that it carries. This carbon could be connected here. All what the carbon will do is to remove one hydrogen and also another hydrogen, so that this one will be bonded in here, forming already a carbon that is attached to another carbon, forming primary carbon. So that is what you call it, the bonding properties of carbon. It could detach its bonded element, like hydrogen, to enable this carbon to be bonded with another carbon. You will be meeting the carbon in many structural pattern. In fact, you will be, I do not know, but if you were only inside the classroom, if we are only meeting face to face, you will be doing these kinds of structure. Pero I, your first experiment will actually be dealing with forming this kind of structures as models. So you will be doing your own models to show the structure of carbon, bonded with many elements. This is the Sp3 hybridization of carbon. You have learned this when you were in your chemistry high school or grade school, showing to you where is the carbon. So this is the 1s1, sorry, 2s1, 2s2, and then the remaining electrons for the 2p and then this could be subdivided into Sp3. So in the ground electronic state of carbon, the S electron was filled first before placing the remaining 2 electrons to the 2p. But in a higher electronic state, the carbon has to fill up 1 for the S, and then the remaining is to fill the other electron shells for the 2p. But in an sp3 hybridization state, all 4 electrons are placed in the sp3. Okay, it is very important for us or for you to understand and review the electronic orbitals of carbon. There are actually multiple orbitals within an atom. Each has their own specific energy level. So if you're going to review your quantum numbers, these are your distributions. Okay? As a review, the n refers to the number, which is called the principal quantum number. And this could only be positive. And then you have the letters SPDF represents the angular momentum quantum number. And they are usually presented to you as your electron dot or the electron shell distribution. The orbital angular momentum quantum number may be 0 or positive number, but it can never be greater than 1. So, negative 1. Sorry. Each letter is paired with a true value for S0, P1, D2, F3. The magnetic quantum number describes the orbital that can range from negative L or quantum to positive quantum. It indicates many orbitals there are, thus many electrons can reside in each atom. So you have to review your electronic orbitals. But in organic chemistry, we will only focus on carbon, hydrogen, sometimes sulfur, sometimes nitrogen, and of course the halides, your FClBrI. These are the common elements that you will encounter here. Not just like your inorganic chemistry that you have to hold with you your periodic table every meeting that we have. But in organic chemistry, you should only be familiar with carbon and few elements like hydrogen, sulfur, nitrogen, and the halides. Okay, this is the breakdown and properties of the subshells of carbon and other elements. So S subshell, P subshell, D subshell, F subshell. So of course, these are their quantum numbers. These are their momentum quantum numbers. Of course, in the S subshell, you have the S orbital, and then you have the 3p orbitals for P, and the 5d orbitals for D subshell, and 7f orbital for F subshell. I hope you can still remember those things that you should have learned in high school chem, especially those who are in the STEM. So Maximum number, you have 2s, 6p, 3d, 10d, and then you have the 14 f orbital electrons. That's why we have 1s2, 2s2, but we could never have s3. And then you have 1p6, 1p2, 1p3, 1p4, but not 1p7 or 1p10 because the 10 will already go to your D subshells. And 14 for F14 for your F subshells. Okay, welcome to organic chemistry. This might be one of the interesting structure that you will see in the early part of your organic chem. This is how your S orbitals are drawn or illustrated. And of course, you have here the illustration of the symmetry of the X, the Y, and the Z for your p orbitals. So this is your p orbitals, p negative 1 position, p, and also the p1. So the difference is for p negative 1, the loops are in the x orbital. For p0, the loops are found in the z line. And then for P1, the loops are found in Y. So I repeat, X, Z, and Y. That is the position of the loops. Okay? And then we have to look at how the D orbitals position its orbitals. Okay, negative 2, D negative 2. The lobes are positioned in X and Y. For negative 1, the main loops, are positioned in Y. Can you see that? Y. And where is this position with? Z. In D0, the blue lobes or the main lobes containing the z orbital or the s orbital is surrounded with the other the other two pairs of lobes. So this one is illustrated with a bracelet or a ring. And then you have also D1. Again, the main is found in the Y. Can you see that? Y. And then the other one is found in the X. So and so forth and so on. Let us try to look in a magnified view. So this is your C orbital. This is your px. The loops are found in the, the X. And then the py, this lobe is found in the Y line or vertical line. And then for PC, you have here this diagonal line. Originally, the P is actually a circle. But since it is passing through lines, the energy is actually half into two. So this one divided into two. So the one half is here and the other half is here. So if these two loops are passing in the X line or in the horizontal line, it is called PZ. If it is passing through the Y line or vertical line, it is called the PX. And then you could also have this. It is also possible to draw that this is bigger and that is smaller, or the other way around. This is smaller and that is the bigger. This is also true here, small and big. Also true here, small and big, or the other way around. So that when placed in its proper structure, you can see here the dark blue as the S, and then you can see here the PX, and then you have the PY, and then you have the PZ. Second period elements, like your carbon, nitrogen, and oxygen, follows these atomic orbitals. Now let us try to look at methane. Of course, you have learned that this is already your carbon, right? But methane has four H's, and H has only one. So more or less, this is how this is how the hydrogen looks like. So the violet there is actually your s orbital, and if we are going to look at if these are the px, y, and z orbital, you could really place here in the py orbital one circle for your hydrogen, and then for px another, and then for your py as another, to have the CH3 formula. But you could also have H4 because of their capacity of having a free for free for hydrogen. Here you have an assignment to review. Valence electron pair repulsion, or the BSEPR, or sometimes we read it as BSEPR. Okay. This is your 1s1, 1s1. If bonded together, you have the 2s2. So if you have hydrogen and hydrogen, this is how it looks like. Okay? But you could also have your p orbitals here. In this case, you have the one p orbital working with an s. And you could also have another p orbital working with another s. And this p orbital could be working with another orbital, which is this one. This is one p orbital working with or bonded with another p orbital. Or you could have y orbital bonded with another y orbital, forming this structure. So if you're going to look at this, it is linear. But if you're going to look at this, it seems like uh, a hot dog ball or two hot dog linked together. So we have here your valence electron per repulsion per carbon. Please read. But the emphasis here is carbon has a valence of 4 and must have a tetrahedral geometry. So CH4 or methane, its carbon atom must have a bond angle of 109.5. Always remember that. You should know that the bond angle for CH4 or methane is 109.5. This is the largest bond angle that can be attained between all four bonding pairs at once. So this could also lead you to the discussion of hybridization. Atomic orbitals themselves to meet Bespar geometry and valence band theory. These are the three types of carbon hybridization. The Sp3 enables the carbon to be bonded with one single bond, all single bonds, but for the case of Sp2, it allows one double bond, hence the remaining two single bonds. For Sp, it allows the carbon to have triple bond. To make it 4, it remains that it has only one single bond. So as an illustration, you have here the overlapping of the different electron cloud formula or structure of carbon. So you have here one hydrogen for one carbon. So that is the CH. This is carbon to carbon. This is CH3 bonded to another carbon. This could be your hydrogen. So and so forth and so on until you will have a very complex structure of double bonds. Okay, this is a simple illustration of the different Bespar geometric structure of carbon, the possible atomic orbitals combined through geometrical structures. Okay, you have to memorize, not only understand, but both memorize and understand the carbon atom hybridization state parameter. So if this is the hybridization state and you are asked of the hybrid orbital for sp3 4, for sp2 3, for sp2. It's very obvious since carbon is 4 valence, so the remaining is none, sp2 1, sp2. The number of groups bonded to carbon, 4, 3, 2 again. So, hence then therefore, the numbers of alpha carbon is 4, 3, 2, the same. And since it has the remaining orbitals, of course, the pi orbital for sp3 is none, and then sp2 1, and then sp is 2. Geometrical structure, tetragonal for 4, trigonal planar for 3, and then the linear for sp2, that is 2. You should understand the logic and you should memorize these things. Okay, this is how hybridization jumps from one electron to another. This was also illustrated from the previous slides. So filling up the 2s, then the remaining 2 for the p, or 1s, and then continue distributing it as 1. So for the ground state, this is the distribution. For the excited state, this is the distribution. Okay, this is now the electron cloud formula for CH4, showing to you where are the hydrogen. The loops working with hydrogen are called the sigma band. The single band are the sigma band. And then in the case of hybridization, this is the final illustration, although the angle is 108.7. That is the sp3 hybridization of methane. And then this is the sp3 hybridization of ethane. You have here already a carbon to carbon bond. That is a single bond. And this is the illustration. Okay. And the hydrogen to hydrogen angle is already 109. And then you have here uh, CH2. This is one bond. This standing molecular structure forms another bond. So there are two bonds already in the sp2. And then for this is the sp2. To illustrate the bond, it is already 120. Last time it is only 109, but now for double bond with single bond, it is 120. So this is supposed to be 120. This one is 109. This is again another 120. The change of the angle prevents a free rotation of the carbon molecules attached to single and then double. Okay, this is still your um, carbon to carbon bond, but now it is the triple bond. Of course, this is the first bond. If you could see here the vertical P and the vertical P. This is the diagonal P and diagonal P. So this Y orbitals here form one bond. Ito, isang band yan. Etong nakatayong to is also forming another one band. And of course, the linear band with another one. And this is their excited hybridized state. The ground, the excited, and the hybridized state. So this is to illustrate the angle 120. So there is no free rotation already in that manner. So this is one band, the violet, and the blue, that is another band, and then the green, that is another band, forming your two, or sorry, triple band. Okay. The sigma band is the antimolecular orbital. Okay, these are still illustration for other elements. Fluorine, of course, this is your carbon. You have here, if this will link together, that is one single bond. But if again it permits this to be bonded, that is a double bond, but that is wrong in that illustration. So these are other molecular illustration, electron cloud molecular illustration for sp2 orbitals. So it is a sandwich band. Sandwich because it is the first bread, of course the palaman, and then the another slice of bread. And this is your sp orbital. It is already coated. So this is your carbon atom. It could be bonded singly, or by double bond, or by triple bond. It could also form aromatic compounds.